Okay, so I'm just going to give you a little bit of a run over of these notes. I believe these are the ones from 2010. And partway down the page you'll see this expression here. Let me get a pen first. So this is the definition of the inverse Z transform. This is a contour integral in the complex Z plane. But not to worry, we don't use that. We actually use partial fraction expansion, just as we do for the Laplace transform. As far as properties of the Z transform go, just to point out a couple of them, this is how the linearity property works. Hold on. So if we wanted to find the Z transform of a sum of signals, we would simply take the sum of the Z transforms, and in the case of the constant in front, we can pull that out in front as well. And so that we just then do a table lookup of these two, and we have the answer. Convolution, very much the same as it is for the Laplace transform. If we have the convolution, so we have a system, so the u of k is equal to the convolution of e of k and the pulse response. But in the transform domain, this corresponds to u of z equals e of z times h of z, where h of z is the transfer function. And then we can just invert u of z to find u of k. Okay, so the time shift property, this is one where we take, this is proof of the time shift property. So if we were to take a shift of n, and this is, this is the two-sided Z transform, so be careful because there's also a one-sided Z transform that just starts at 0. And this is generally what we use in our systems theory because we're looking at time starting at 0. So be careful about this. So this one's for the two-sided Z transform. So we have the Z transform. So I create a change of variable here. I equals k minus n. So now this becomes f of I. And then k is equal to I plus n. And so the limits stay the same, infinity to infinity, so it's pretty much the same. Infinity minus n is the same as infinity, where n is a finite number. And so now then we can pull the z minus n out front, and then this is the definition, just with a different index variable of the original Z transform. So if it's a delay, you pull out a factor of z to the minus n, where n is the number of delay units. And if it's advanced, then it's of course z to the positive n. If it's a one-sided Z transform, it's a little bit different here, because then what we have, we no longer have infinity here, so this index here changes when we do this substitution. So we can take this one, which is the Z transform, and then we can subtract out the initial conditions. So this starts at, actually we have to add them in. So it starts at minus n. So if we start at 0, we have to add in the one for minus 1 and the one for minus 2. And then all the way on up to n. So you'll see that there's an expression that is different if we're shifting a one-sided signal. Final value theorem. Sorry this is going quickly, but you can always watch it over and over again. The final value theorem is stated this way. The trick is you have to make sure that all poles of z minus 1 times f and c, f of z, have to be inside the unit circle. Because if they're outside the unit circle, then the final value is infinity. So the problem is that you could get an answer using this formula, but if the poles are outside the unit circle, that answer is wrong. So just be careful about using it this way. Okay, I will stop this video. The next one will be on partial fraction expansions and inverse Z transforms.